Welcome viewers to E-Pathasala course content for PG students of architecture. We were discussing about various data structures which are present in GIS, namely the vector and raster. I just given an introduction to vector data model and we will see in detail about a vector data model. So, what you should understand is that how you can relate the objects in GIS. So, that is what is the most important aspect. A vector data model enables us to do that, so that we can have a find out or how you can examine the relationship between variables in a single coverage or among various coverages or different coverages. Normally, every kind of software, every software will have what is called as a topological data model. So, this is what is the one which is most commonly used, and that will have various operations to represent vector data. What it does is that this develops or it incorporates network say relationship among coordinates and measurements. So, this is what is you have to bear in mind. So, that is what is the important aspect of your vector data model, where in which you talk about the topological data models. Let us see in detail the vector data, which I already told you. I will just give you a brief again. These are normally referred to as arcs, and they have a string of vertices terminated by a node. Of course, a node is nothing but is a vertex that starts or ends an arc segment. Of course, point features are normally defined by one coordinate pair, that is a vertex, and I also told you that polygon features are defined by a set of closed coordinate pairs. You should know that in vector representation, the storage of vertices for each of these features is important. In fact, that is what I was telling you. You can input the data or get the data from various sources and then incorporate in GIS, but you should also know how to store them. So, these vertices for each and every feature is so important, because that will also have the connectivity between features. For example, if you have two features, two objects, for example, if you have something like two polygons or two lines which are intersecting, two polygons will have a common line in between. So, when you have two adjacent polygons, you will have a common line between the two polygons, or you have something like intersection of lines, somewhere in between you will have the common point for both of them. So, that is what is an important aspect as far as your relativity or the connectivity is concerned. Bear in mind that these like segments or line segments are, it is just defined by a starting point and it has got a direction and a length, which I told you about a line data. All the points which are stored in real earth coordinates, which it uses this particular model uses that analogy of real world coordinate system. So, otherwise it will be very difficult to retrieve the data back, and obviously lines and areas are built from say sequence of your points in order. Line will have both direction, have a direction based on the ordering of the points, as well as it will not have anything like a magnitude, whereas straight lines and the curved lines, it all depends on how you create. A straight line, it is just by joining two points. A curved line, what will happen, obviously when you are just trying to change the direction, when you want to have a curved line, the direction changes. Similarly, in the case of a polygon also, there will be direction change as well as your magnitude. So, it will change in that in both the direction and magnitude. And most importantly, all the vector models are capable of storing the data about their topology. Let us say just about this vector data structure. Let us see the graphical depiction of simple vector data. How does it represent, how do you get the data in that form? For example, let me show a kind of a parking lot. A parking lot is more of a, say in this context, a rectangle aspect or an object. Normally, when I want to show this one, I just draw from here to here and then come back here and close it here. This particular area is earmarked for cars, this for buses, and this is for staff. Do not worry about what exactly we are using, just for the sake of it, understanding point. Now, when I take the polygon file, and I also should remember how in which direction I am supposed to digitize the data. From this direction, I just go along, go like this, go like this, go like this, and then come back. Of course, sometimes it has no significance, but many times it will have a very important significance, especially in the case of say drainage system. If somebody is working on say drainage system, it is very important, your direction of drainage is important, because that will decide the flow direction also. So, you should always bear in mind that we should digitize the actual drainages. I am talking about the drainage system in nature, or even in the case of your planning in a city, because if you can digitize the drainage line according to the flow of direction of water, it will become much easier for analysis. Otherwise, you have to change them at the time of analysis. So, try to maintain a particular direction in such a way that it represents the flow of direction of water in a case of a drainage. In a simple polygon, it may not have that implication. So, this is the direction of your digitization and goes on like this. And this polygon file, you have a ID, and that ID is this has to tell you the car, this is for the staff, and this is the buses. So, you can also have any other ID. So, what we will do is that cars are normally represented say points 1, 2, 3, 4, 8 and 9. You can see here 1, 2, 3, 4, 9 and 8 or 8 and 9. So, this is your car aspect. Then the staff part of it, we have 4, 5, 6 and 9. When it comes to buses, 6, 7, 8 and 9, and it just closes here. When I take the representation as such, if I consider this 0, 0, this has say 20, 20 or 100, 100, how does it go? For example, this one value 1 and the x will be 0, y will be 0. Obviously, when I come to 2, x will be 0 and then y will be 10. When I come to the second aspect 3, it is 0 and 30 and so on and so forth. We just find that it varies over a distance from one point to another point, the values will be changing. And what are the various critical issues what we face in the form of say, in the case of say your vector data. The most important aspect in vector data is your topological consideration. Topology. What is topology? It is a mathematical way of connecting features on the surface with respect to the map. Every object, when I am just trying to show, that is what I think you remember when I told you about difference between a drawing and a map. When I am trying to generate a map, I will have to have some consideration to the details of connectivity, how an object is connected with each other. And when I am representing the objects in real world coordinate system, I will have to follow the topological rule. Vector data follows the topology to a precise level, so that I do not get any kind of error whatsoever with respect to the quantification of data. Qualitative representation is different from quantification. When I want to make measurements on the earth's surface, I use some device, I go to the field and make a measurement. When I want to make measurement on a map, definitely I should make sure that the data is properly connected with each other. Of course, we have other aspects also in topology, I will tell you later. So, to make any kind of quantitative analysis on a sheet of paper, that is a map, you require topology. So, I was telling you it is nothing but the relation between various features which are present, and they have a specific quality. It is otherwise called as connectivity of data, directionality of data, contiguity or your adjacency of data, and we have the containment or the objects which are present within each other, a polygon which is present within a polygon. So, that is what are the three aspects. In fact, I used to call it as a 3C concept. Of course, directionality is another aspect which will not be directly having a bearing on the data. The 3C concept, namely the connectivity, contiguity and containment. So, this is the 3C concept in topology. If one can clean the data or build the data, what we call in terms of your GIS, the data will get or it will be free from all kinds of errors. So, that is what is the importance we have for topology. So, we have to remember that lines can never overlap without a node in a topological data structure. While drawing, I may just draw a line like this, one line this, one line like this. But when I say or build a topology or create a topology, the lines which are drawn like this and like this are always intersecting at a particular point, normally the node part of it. It cannot simply overlap with another without a node. So, that was the importance of your set topology. The factor of say scale, as all of you know very well, scale plays a very important role in any kind of map making. The greater the accuracy with which you do, the better will be the output. So, what will be the impact of scale on say vector data? It determines the precision with which the line feature can be represented. So, definitely the scale will be a factor there, and more importantly, when I want to represent a curved line. So, I am not trying to say methods of collecting data is wrong. For example, when I am using say something like surveying data using a total station, the disadvantage in that, in the case of your total station data, is that invariably it will be a kind of joining of points. What they tend to do, they take the total station, go to the field, go around an object, collect points and join the points. Obviously, what will happen? It will become more of a non-regular object which are connected by lines. But when I want to have a smooth surface, what is that I should do? Even in that context, they also should collect more number of points. So, the greater the number of points within a line, the greater will be the curvature. As long as there is no curvature, we do not have to worry. But when an object takes a curve, it is very important for you to have more number of points in between. So, that is what we call it as more vertices allows for more line curvature to be represented. And you should know that this scale is always related to the spatial accuracy in GIS. So, when I have a coarse scale, for example, 1 on 50,000, 1 on 250,000, of course, they are all relative in nature. With respect to 250,000, 10,000 becomes a larger scale or a fine scale. With respect to 10,000, 5,000 will become a larger scale or a fine scale. So, with respect to 5,000, 10,000 becomes a coarse scale, because it is only relative scale. So, the coarser the scale, the lesser the feature and the accuracy. The finer the scale, the greater will be the number of details which can be obtained, and the greater will be the accuracy of representing the data, even in the case of your vector data. Of course, when you want to represent the same feature from different sources, this is a very crucial point. When I have data which is being represented of the same area from different source. For example, data can be obtained with respect to geological aspects. Nobody would have prepared a geological map there. So, that map may be available in say 500,000 scale or 250,000 scale. But when it comes to soil data, again that also may not be available in the scale of a requirement. I may be preparing a very detailed drainage map on a 1 on 50,000 scale. But when I want to represent the same for the same area, geological aspects as well as soil aspects, I will not have that liberty. So, when I have two different sources of data, I will have to manage that very efficiently in GIS. So, it is very important to have similar scales when you are trying to show different thematic details of the same area. So, that plays an important role. So, we will have to integrate the data in a proper fashion. When you just look at the data, I will just tell you what all I have told you previously, I will just show you as a depiction here. Various details are given, and this is a simple map. It contains n number of polygons. You can see 1, 2, 3, 4, 5, 6, so many polygons are there, each represented by different color, just to show you difference. This in general is called as a coverage. It will have a set of map features, and it will also consist of say annotation or text features. Annotation is nothing but your text detail. This is a polygon, this is another polygon, and it is, I was already telling you, it is bound, a polygon is bound by what is called as your arc. We will see the details little later. So, enclosed by arcs, and what are again arcs? It is nothing but line segments forming the polygon borders or individual linear features. Even for example, you can take this one or a street network. Points here, it is nothing but your simple single coordinate pair. This could be a point data. This could be a discrete point which may be representing the center of this polygon, or it could also be text detail. If you want to give a position of a text, where you want to put your text data, this will be important here. Of course, when I talk about the nodes part of it, you should know this is what I was telling you, the node. For this particular arc, this is the beginning node and this is the ending node, and this is your vertex or vertices if it is in plural. Of course, with this you can call it as vertices, node, vertex 1, vertex 2 and the node. And you see here there are no vertex, because there is no change in direction. This is what I have been telling you. When there is a change in direction of the linear aspect, then a vertex is introduced. Node, vertex 1, vertex 2, node, and this is straight. And you see here there are so many vertices in between this node and this node. So, this is what you have to remember in mind. So, all the details are given in this particular drawing. Of course, you also have one more point, namely the tick point. This is what is nothing but the registration of a control point. When I want to translate the data from a sheet of paper, that is your hard copy, to a soft copy by scanning, and then take the scanned copy into GIS, make this GIS system to understand what exactly is present where, I will have to register the data. This we have seen in the case of your registration of your map. So, in that context, all the control points which are given here, which are or the corners or anywhere in between, any point you can take, they are called as ticks or registration control points. See, a topological model, I was telling you about the directionality, the connectivity, adjacency or the containment, or we also call it as the nestedness, what is present a polygon within a polygon, because that will only decide the quantitative aspect of that, length of a line, perimeter of an object or a circle or any other regular or non-regular feature, or it could be aerial aspect, area of which is being occupied by a given object. For all these things, topology plays an important role. As you can see here, very importantly, we call it as the adjacency, nothing but I will just give it just, and then we will go to the figure there. Connectivity, connectivity between one point and another point, that is what is connectivity. That is, if I am talking about something like, say, in any place, given place, say something like India Gate to another point, how is that particular point connected with each other? Or we talk about the airport, New Delhi airport to the railway station. Definitely you know that you can start from the railway station and take n number of routes to reach airport. You agree with me? If you want to go from railway station to airport, you may have different routes, and each of them are connected, unless otherwise they are not connected, it is not possible for you to reach. So, the connectivity depicts or shows that what is the connectivity between one point and another point through what? Various arcs. Then we have what is called as the adjacency, spatial adjacency or contiguity. I was talking to you about the 3C aspect. Connectivity is 3C and the second one is your adjacency. Spatial adjacency is one which aspect is present or which object is present adjacent to what object. To reach from one point to another point, you may have n different areas. So, when I say that, what is which area is present adjacent to which area? The contiguity or the spatial adjacency. Then we say containment. What object is present inside what object? For example, let us take a room. A room is one polygon. Inside a room, you may have a table or a chair. That means, this table or chair is occupying a part of the area of the room. If I take the room, for example, 10 by 10, within that a table of 3 feet or 2 feet length by 2 feet or 3 by 2 table may be occupying. That means, that particular area occupied by the table is not revocable as long as the table is present there. That means, the object is present there. You have a polygon room, you have another polygon 3 feet by 2 feet a table or 2 feet by 2 feet chair, and you should understand that contained this particular table is within a room polygon, an object which is contained within another object, containment. So, this is the third C. Please bear this in mind, this is a very important aspect in your GIS, topological aspects. So, coming back to this one, let me take 1, you see here, and this point 1 left of the polygon is your A, right to polygon is 0, nothing is there, 0, and then it is starting from node C to node A. Of course, you can also say A to C or C to A, does not matter. So, let me say if the starting node is C, it just goes like this is a vertex here and it comes here. Point number 2, so wherein which you have this line, it again you have to the left of it is A, to the right of it is your B. So, this is the polygon B, and it starts from B to C, this line B to C. So, this is to the left of it, to the right of it. So, if you start building the adjacents, that is what I was telling you, this particular line, what object is adjacent to the left, to the right, spatial adjacency, connectivity between 1 and so this is the point. If you want the third line, fifth line rather, and all of them are intersecting at this particular point, line 3, line 2 and line 1. So, if I want to reach say this particular point, I can start from here, go like this, come like this and come to this point, or I can start from here, go like this, come back here, or I can start from here, go along this particular point, go around and then come back here. So, this is the connectivity, this is the adjacency. When I talk about your containment, what object is present within another object? You should understand that object D here is present within the object P. Obviously, though this B is occupying the entire space, you should remember object D is occupying this space. Then definitely B will not have or will not include this area, because it is occupied by some other object, unless otherwise it is cleared. In our context, normally let us say in any given area, what is present today may not be present tomorrow. A plot of land, when I am planning to construct a building, I want to prepare a plan for that. A plot of land may be containing an old building. In a record, older record, that particular plot of land will be showing a building already present there, but I am not interested in, because I know pretty well it is not possible for me to construct another building without demolishing the old building, is not it? You agree with me? In that context, the containment in GIS is that the building plot, the original plot will contain a old building. I am supposed to demolish this or remove that and then go for a new building. So, when I demolish, what will happen? The entire thing will become one particular plot, as you have just seen in the case of your plot or your polygon B. The D is the building. Now, when you remove this D, the entire thing will become one single polygon. You see how important containment, what is present which is within another polygon. So, that is what you call as the containment. So, the connectivity, the containment and your contiguity forms the topology, and that is an important aspect. Of course, I told you about the directionality, which direction it moves. So, you should know that from where the origin has started, where it has ended, how it is moving around. So, that is the direction part. So, these 4 becomes 4 components of your topology, the most important aspect. Why do you think the topology is important? Why topology matters in any context? It removes or it helps us to remove the error or reduce the error, or to automatically remove the error detection, automation and elimination. So, that is one important aspect. Then when I am trying to make changes or when I am trying to correct the errors, I can also think of snapping the data. I can give a tolerance limit to the system. I can explain and tell the system, if you give a tolerance of 0.001, whatever is that distance, 0.001 millimeter, 0.01 millimeter, 0.02 millimeter, whatever is the tolerance you want to give, you can give that. Obviously, what will the system do? It will automatically snap that. If I do not give the tolerance limit, it will simply try to collect the data or try to link the data which are not relevant to the adjacent aspects. So, what we do is that we give a tolerance limit to the explain the system, this is what is my tolerance limit, kindly snap the data. So, automatically data will be snapped. So, to remove an error which is present, we will see that a little later. Just to get an idea, we give a tolerance limit and ask the system to snap the data. And very importantly, we will be in a position to go for a overlay analogy. Please remember that I was telling you about a room consisting of n number of objects. This room, the outline of the room will become the outline of the polygon, that is one layer. The second layer will be your various chairs which are present. The third layer will be your various tables which are present in that room. So, when I am trying to overlay one over other, I need some topological relationship. Otherwise, what will happen? I will be overlaying, if it is not properly connected, the tables and chairs will get clashed, isn't it? So, what is that we are supposed to do is that we need to have a topology. When I have the topology, overlay becomes easy. So, the first line or the overlay layer will be your polygon depicting the boundary of that room. The second layer will be the your various chairs which are present. So, when I overlay the chairs or the tables which are present in that room, it will occupy a space and it will not allow other objects to occupy that space unless otherwise it is moved. So, the chairs will occupy its own space, the tables will occupy its own space, and the entire thing is bound by the polygon of the room. So, that is what is the analogy you use. So, overlay analogy for any kind of representing the object to its original position. And that finally, it will help you to analyze the data spatially. If you want to find out what is the distance between one object and another object, how do I plan to plan a kind of an auditorium? I know that when I want to plan an auditorium, that there should be some relationship amongst the objects, various chairs which are present. I want to put them together. So, I will decide between one chair and another chair what is the distance is required. So, in a given row, I may have n number of chairs, 10, 15, 20 depending upon the size of the auditorium. Then I may have the podium, I may have the main dais. So, on the dais I may have various other features which are, see, you can also talk about the directionality. Chairs which are facing the dais will be in the opposite direction the chairs which are present on the dais, isn't it? So, obviously, here the position, its connectivity and containment. Containment is the chairs within the table. See, everything is connected to one another. The containment, the contiguity. So, which chair is present adjacent to which chair? And if you have any table, sometimes we may also have an auditorium table and chairs together. Then the dais. On the dais you may have or may not have a podium, you may or may not have the table. If you have the table, what is present where? So, this is what the beauty of your topological relationship. So, that is how we try to develop that. I was telling you about the snapping or your corrections which are being normally done. So, this is what is your unsnapped node. So, when I give a tolerance limit, this will get automatically snapped and this will be hanging. This is what we call it as undershoot and overshoot. Sometimes the lines may overshoot with another, sometimes may undershoot. This is undershoot as such, but if the tolerance limit is not given properly, this will not get attached automatically. So, when I am cleaning the data or building the topology, I should understand give based on the errors what we make, either it is going to be very close or far away. Similarly, the bounding rectangle, what you have here, a rectangle you have the x minimum, y minimum, x maximum, y maximum. If I just define this, whatever you try to incorporate will all be incorporated inside this one. So, but this will end about the topological aspects. Next we will discuss about the coverage models and what are the various models which are present in GIS. Thank you.